Today we're going to start our discussion of chemical kinetics, and kinetics is just another way of saying studying how fast or slow a reaction happens. And so what I have shown here on the cover slide for our presentation today is a reaction that starts out with all purple reactants, and then as it progresses, if you were to plot the concentration of the purple goes down as they start to react, and then green ones start to appear as they are the products that are formed. Okay, and so this is just a plot of how that concentration is changing over time, which is a measure of rate. So as I said, a reaction rate is just a measure of how fast a reaction occurs. And so what I have here is a table that shows us the concentrations changing over time for a particular reaction. So the reaction is H2 plus I2 goes to 2 HI molecules, okay? And so when we start, we have some H2 and we have some I2. We have 1 molar of each of them, and we have no HI. Those are our products, and we haven't formed anything yet. And that's at time 0. So at 10 seconds, you can see that some of the H2 and I2 has reacted, and some HI has formed as a result, all right? So as the reaction proceeds, the amount of hydrogen gas is going to go down because it's a reactant, and the concentration of iodine gas is also going to go down because it is a reactant that's being consumed. And then as the reaction happens, the concentration of HI, or hydrogen iodide, is going to go up because that is the product that's being formed. So it starts at 0 and it continues to rise as the reaction progresses. Okay, so this is just that same table. I just shrunk it so that we could fit it onto the slide here. So if we compare the rates of H2 and I2 consumption, you can see that they are the same. So we have, we drop from 1 to 0.819 to 0.67 in both cases and the whole way down. So at 100 seconds, we have 0.135 left of H2 and 0.135 left of I2. So the rate of change of those two reactants is the same, and that is because the ratio in the balanced equation is 1 to 1. So if we use up 1 H2, we also use up 1 I2. Okay, now if we compare H2 to HI, you can see that the HI has a coefficient of 2 here in our balanced equation, and so what you would expect is that when you use up 1 H2, you're going to form 2 HIs, and that's exactly what you see. So if our rate of change for H2 is negative 0.0181, which we have here in our table, and the rate of formation of HI is 0.362. Or sorry, 0.0362 over here. Okay, which is twice the amount of H2 that was used up. And so that, again, is because of the coefficients in our balanced equation. So if we compare the rate of HI formation at 10 seconds, at 100 seconds, which is greater. So at 10 seconds, that's the one I already just pointed out to you, the 0.0362. That's the rate of formation of HI there. And at 100 seconds, it's only 0.0060. And so the reason is because as our reaction progresses, we're using up reactants, and so it's going to start to slow down as those reactants disappear. Okay? And then what does the value of the reaction rate approach as you near the bottom of the table? Eventually we get to the point where the reaction is going to stop, and so the rate of change is going to be 0. And so you can see that it's getting progressively slower and slower as our reaction progresses. Now there are 2 basic ways that we can report our reaction rate. We can do an average reaction rate, which is what was shown in the table before. So that's in the period of time between 0 seconds and 10 seconds, what was the rate of change? And so we average that rate over that time period. An instantaneous reaction rate is a little bit different. So for example, on the front page, I had a graph that looked like that, right, for the product that we were forming. So in that case, if we wanted the instantaneous rate, we go to the point on the graph that we're interested in, and then we draw a line tangent to that, and the slope of that line is going to be our reaction rate at that specific instant in time. Okay, so it's important to know the difference between the two. The average reaction rate is going to be easier to measure because you could measure a concentration at one time and measure it again at another. But if we were going to plot the rate or the change in concentration like I did here, you could take the tangent and get an instantaneous reaction rate at any point along that curve. And they should be similar. Okay, so now if we have a reaction, a generic reaction here, where we have reactants A and B with coefficients little a and little b, going to products C and D with coefficients little c and little d, then we can write the rate using the equation here. And so the reactants are always going to be disappearing, and so you're going to have a negative there. And I just noticed that there's a typo, which is probably also in your notes. So these should actually be positive. Okay. And then the products are going to be forming, so the rate of formation of those will be positive. So now let's use this equation in an example. So if we consider the following balanced equation, we have H2O2 plus 3I minus gives 2H plus I3 minus plus 2H2O. Okay, in the first 10 seconds of the reaction, the concentration of I minus dropped from 1 molar to 0.868 molar. So it wants us to calculate the average rate of the reaction in this time interval. So the rate for the reaction is going to be equal to negative, because this is a reactant, so it's disappearing, 1 over the coefficient, which is 3 for iodine, so 1 over 3, times the change in concentration of I minus divided by the change in time. And so the change in concentration of I minus, the final concentration is 0.868, and the initial was 1, so it'll be 0.868 minus 1, divided by the change in time, which is 10 seconds. Okay, so if we multiply all that out, and in kinetics reactions, it's really important to keep your units, because the units of different things can change depending on the reaction, so it's important that you keep track of what all of your units are. So if we multiply those out, we get 4.4 times 10 to the minus 3 molar, which is that capital M, per second. Okay, now if we predict the rate of change for the concentration of H plus during this time interval, so the rate of concentration of H plus change will just be the change in H plus concentration over the change in time. And we know that the rate of the reaction is going to equal negative 1 over 2 times that value, because the coefficient of H plus is 2 in our balanced equation. So if we solve for the change in H plus over the change in time, we get negative 2 times the rate, and above there you can see the rate, and we plug that in, and we get negative 8.8 times 10 to the minus 3 molar per second. All right, now let's talk about rate laws. So what is a rate law? A rate law is basically just a mathematical way for us to represent the relationship between the concentration of the product or reactants and the rate. So the general rate law is written as rate equals K, which is the rate constant, times the concentration of A, which is one of your reactants, to the N. Okay, so I already said the rate constant is K, and this just is what it sounds like. It's a constant that tells us the relationship between the rate and the concentration. So it's just a number that you can solve for experimentally if you do a reaction. And then the reaction order is this little exponent N. Okay, and we're going to spend the next couple of slides talking about what reaction order is, and it basically tells us how much the rate depends on the concentration. And it is usually, though not always, but in our case, we're going to say it is either 0, 1, or 2. So a zeroth order reaction is a reaction that does not depend on the concentration at all. And this is fairly unusual, but it usually, and what it implies is that the concentration doesn't matter. And so if you were to look at experimental data, And it's important to note that the only way you can determine the order of a reaction is to look at experimental data. You can't look at the balanced equation and figure out what the reaction order is going to be. So if we look here, if we change the initial concentration of A in our zeroth order table up here, so we're looking here, if we change the concentration of A from 0.1 molar to 0.2 molar to 0.4 molar, the initial rate remains unchanged. And so that tells us that this is a zero order reaction. So the rate law for a zero order reaction is just rate equals K times the concentration of A to the 0, which is just 1. So the rate is just equal to K. It's a constant, it's always the same. For a first order reaction, what you can see is that in our table here, when we go from 0.1 to 0.2, that doubles the concentration of A. We also double the rate. And then if we go from 0.2 to 0.4, the rate doubles again. Okay, so for a first order reaction, the rate law is going to be the rate equals K, which is our rate constant, times the concentration of A to the first power, which is just the concentration of A. Okay, and then the last one we have here is the second order rate, second order reaction, and the rate law for this one is going to be the rate is equal to K times the concentration of A squared. And so you can see here, if we double the concentration, if we go from 0.1 to 0.2, we actually quadruple the rate. Okay, so that's not times 2, it's now times 4, because 2 squared is 4. Okay, so now we're going to take a look at, if we have experimental data, how can we determine which of the reaction orders we have. So if we consider the data below showing the initial rate of a reaction for a single reactant A, forming products at several starting concentrations, what is the order of the reaction, and write a rate law for the reaction, including the value of the rate constant K. So now we want to start with our general rate law, which is that the rate is equal to K times the concentration of A to the N. Okay, and we want to find both K and N in this case. And so if you remember back from math class, if we have two variables, we need two equations that we can use together to find both of those variables. But luckily, we have three different values for A and for the rate that we can plug in. So we're just going to pick the first two. It doesn't really matter which one we use. So we know that 0.0530 is the rate when the concentration of A is 0.1, and so we want to do 0.0530 equals K times 0.100 to the N, and then we're going to use the second set of numbers to get 0.0763 is equal to K times 0.120 to the N. So now we have these two equations, and it's not like solving just two normal equations because we have an exponent here, which makes things a little bit more complicated. So what we're going to do is we're going to divide these two equations so that the k's cancel out. So if we take the one side divided by the other, we get 0.0530 divided by 0.0763 is equal to K over K, which is just 1, times the quantity 0.1 divided by 0.12, all of that to the n power. Okay, and you can get to this based on the rules that you learned in math class about exponents and multiplying and dividing. Okay, so if we divide out on both sides, we get 0.069 is equal to 0.833 to the n. Okay, and I told you that sometimes n is different than just 0, 1, or 2, but in all of the cases that we're going to look at, it's either going to be 0, 1, or 2. So if you were looking for a number that was not one of those, then you could take the log of both sides to solve for the exponent, but I'm not going to go through all of that. What we're going to do is just say, okay, it's clearly not zeroth order because when we change the concentration, the rate changes. So we can eliminate that. It's not 1 because 0.833 to the 1 is going to be 0.833, right? It's not going to be 0.069. Okay, so then that leaves 2, and we don't want to double check and make sure that when we put 2 in for n, we do get that 0.069, and that is what we get. You can check it on your calculator if you don't believe me. Okay, and then, so now we know our value of n is equal to 2. So now we can go back up to either of these equations and plug 2 in for the n and then solve for k. And so if we do that, I'll just do it for the first one. 0.0530 is equal to k times 0.100 squared. And if we solve that, we get k is equal to 5.3. So that makes our rate law. The rate is equal to 5.3 times the concentration of A squared. Oh, and one last thing, we need to include the units for our K. So if we look at the units for the equation we just solved, the 0.0530 is a molar per second, and our concentration is in molar, but we've squared that value, so we have molar squared over here. So to get all of those units to cancel out, we can divide both sides by molar squared to figure out what the units for K should be. All right, and that's going to give us units of per second per mole, or second to the minus 1, molar to the minus 1. And these units will be different if you have a zeroth order reaction or a first order reaction instead of a second order reaction. They'll always be these units if you have a second order. Now if we have a situation where we have more than one substrate or more than one reactant, then the rate law gets more complicated. So you can continue to write out the concentration of the reactant to an exponent for all of the reactants in your reaction. And so then you use the similar process to figure out the reaction order for each of the reactants using the steps here. So first you want to identify 2 experiments in which only one single initial concentration is different. And so I'm going to just follow the example down here as we go through these steps because it's a little easier to understand if you're actually going through it. So here, for example, we have the concentration of NO2 doubles from here to here, but the concentration of CO doesn't change. Okay, so the concentration of CO isn't changing and therefore is not affecting how the rate is changing, and so you can use these two concentration measurements to figure out what the order is for NO2. Similarly, you can use the one that's here and the one that's here because they don't change for NO2. Then you can use those to figure out the order for CO. Okay, so first let's figure out what order we have for NO2. So let's start with our general rate law. So our rate is going to be equal to K, which is our rate constant, times the concentration of NO2 to the X, times the concentration of CO to the Y. All right, now we're going to just use the data from these first 2 rows here in our table. So we have 0.0021 equals K times 0.010 to the X times 0.010 to the Y, because that's our concentration of CO. All right, and then for the second row, we get 0.0084 is equal to K times 0.020 to the X times 0.010 to the Y. And now when we divide our 2 equations, not only are the K's going to cancel out, but the concentrations from the CO2, which are to the Y power, that's also going to cancel out. So the only thing we need to solve for once we do that is the X. So when we divide those 2 together, we get 0.25 is equal to 0.5 to the X. All right, and if we square a half, that's going to give us a quarter, which is here. So our X is equal to 2, so we know that this reaction is second order in NO2. Now we're going to go through the same process for the CO. So now we're going to use the second and the third row in our table here. Okay, so we get 0.0084 is equal to K times 0.020 to the X times 0.010 to the Y. And then for the third row, we have 0.0084 is equal to K times 0.020 to the X times 0.020 to the Y. And in this case, when we divide our 2 equations, the K's cancel and the NO2 term, which has the X in it, also cancels out. Okay, so here we end up with 0.0084 divided by 0.0084, so that's 1, and then you divide 0.01 by, 0.01 by 0.02, you get 0.5 again. And you'll notice that the rate didn't change even though we changed the concentration of CO, and so that tells us that this is going to be zeroth order, but mathematically speaking, having y as 0 is the only way you can get 1 on the other side of the equation. So we know our y is equal to 0, and we already found our x is equal to 2. Now, just like we did on the previous slide, you can go back and plug in the x and your y to any of the equations you've used. So let's just use the one we have here. 0.0084 is equal to K times 0.020 molar squared times 0.010 to the 0. So that's going to cancel out. Okay. Now divide both sides by 0.020 molar squared, and you get K is equal to 21 molar to the minus 1 times second to the minus 1. Okay, so our rate law is going to be rate equal to 21 molar to the minus 1 second to the minus 1 times the concentration of NO2 squared. For this particular problem, I didn't realize when I made your note packet that I had stuck one in accidentally that has a fractional rate. So first let's write the general rate law. So we have two reactants here, so the rate is going to equal the rate equals K times the concentration of CHCl3 to the X times the concentration of Cl2 to the Y. And it turns out that Cl2, that Y value, is not a whole number. This is one of those weird ones that you wouldn't need to do on a test or on the AP exam, at least not to my knowledge. But if I told you, as I'm going to now, that that Y is equal to 1/2, then you should be able to complete the rest of the problem. So take a moment and pause here. What you're going to need to do is solve for X first, and then solve for K, and then write out your value for the rate law. And then once you figure that out, play, and then see if you got the same thing that I did. Okay, so the answer that I came up with is the rate is equal to K times the concentration of CHCl3 times the concentration of Cl2 to the 1/2. All right, and the K that you should get is 3.5 molar to the 1/2 times second to the -1. Molar to the -1/2 times second to the -1. So that wraps up our discussion of introduction to what reaction rate is and how to write rate laws. And we will do a lot more practice of these in Mastering Chemistry, and then also in some practice old AP questions.